All right, one more time. So reaction number 3, again, you haven't learned this in lecture. We never taught you that. That's why I'm about to tell you. Okay. This reaction is one of the named reactions. The name reaction means people discover it, they put the name on it. All right. You might be familiar with Williamson synthesis. Okay, we do SN2 making ether. So that's another name reaction. Anyway, so this reaction is called Woodward dihydroxylation. So adding 2 oxygen onto alkene. All right, so we have to talk about this first. All right, let's talk about, so look at the reagent real quick. So we add silver acetate, iodine, acetic acid, and water. Okay, that's the first step. The second step is a hydrolysis. Use 10 molar sodium hydroxide, pretty concentrated. Heat it up and heat up the reaction, speed up the hydrolysis. All right, the first step goes like this. All right. Iodine, just like bromine or chlorine, right? So form a 3-membered ring intermediate, look like that. All right. So top phase, bottom phase, doesn't matter. I show you the bottom phase. And then the acetate ion, silver acetate, split in solution. So we have acetate ion, that's a nucleophile. Have to attack from the other side. Okay. So this one is bottom phase. So this guy acetate approach from the top phase, look like that. Now the silver though, what does silver do? Maybe you remember the solubility rule in Gen Chem 1, silver and group 7 precipitate. Okay, silver ion that floats in the solution will get nearby this compound and make iodine a much better living group. Iodine is already a good living group, right? But adding silver gonna about to pull iodine comes out, make iodine even better living group. The next step, this is what happened. All right, this one new. Take a look. Take a lone pair from double bond. Take this oxygen, attack that carbon. Use one of the pi bond, attack the carbon. So we get cyclic acetosonium ion. All right, so that's the intermediate. All right. Now this intermediate is in resonance. Okay, have a resonance structure. So the carbon in the middle, that's the electrophilic. All right. Now, if you run this reaction, okay, again, the goal is you look to the TLC result. You get syn-addition, anti-addition, or mixed addition, right? And then you have to propose it. Now, let's say I'll show you how this works. For syn-addition, let's say you get syn product, all right? The 2 oxygen on the same side, all right? You have to think about the intermediate that leads lead to the syn-addition product, okay? Now, if I look right here, so I'm about to show you my proposed mechanism. You can use, but you should not use it. I'm not saying this is correct. All right, I'm just showing you. All right, I have to think about, all right, the 2 oxygen for syn-addition have to be on the same side. Right now, it's already on the same side. Well, what should I do? I should remove this group right here somehow. Okay, so I'm gonna go like this. I'm taking water, attack that electrophilic carbon. All right, proton transfer, remove that proton, you get this guy. Add proton on this oxygen right there. All right, what has happened? Do not put water attack on in either of this carbon. If water attack right now, it's going to be an anti-addition. Because right now the both of these 2 oxygen are on one phase, on the top phase. The new incoming nucleophile, we have to go to the other side. Okay, otherwise you're going to get the trans or anti-addition. So keep it like this. All right, let's see what happens. So put the bond down here, cut this bond, so you get look like a almost like an ester group. Proton transfer, remove that proton, and you get one of this intermediate. Okay. The last step is hydrolysis. So take hydroxide, attack that carbon, right? And at the very end, so this guy comes off, and I get this guy, syn-addition, something like that. There are multiple steps in here in hydrolysis. Okay, but I just show you. Let's at least give you an idea. Well, if you get the syn-addition, you need the intermediate that leads to the syn-addition product. And I see this compound right here already have 2 oxygen on alkene. Well, leave it like that and remove everything else. Okay, so this is my proposed mechanism. I'm not saying this is correct, but this is my proposed mechanism, just to give you some example. Now, if you were, let's say you run this reaction, spot on TLC, and you see anti-addition, what you're gonna do? If you go back to a few videos earlier, right, when we talk about the anti-addition, what controls the stereochemistry of the anti-addition? The 3-membered ring. like that. All right. So I look right here. Well, I'm going to need a nucleophile attack on the other side. Right now we have cis right here. Now these two are cis on the one phase, and I need another oxygen on the opposite side, opposite phase from the bottom. Well, this is what I'm going to do. Take the nucleophile, which is water, attack on one side like that. So the whole thing, this group right here is on the top phase. So the incoming water have to go to the bottom phase. Look like that. If you remember the three-membered ring intermediate block one side of the nucleophilic attack, this guy do the same thing. All right. And then proton transfer. So remove that proton, add proton on the other oxygen right there. And then hydrolysis. Oh, I saw it. My bad. I said it wrong. So remove that proton till you get this compound. All right. And then do hydrolysis. Remove the ester, the acidic group. Now, if you get the mixed addition, what intermediate you would like to propose? The carbocation. Take a look. I'm proposing a carbocation now. Right there, we have a carbocation. Water attacks. Right. So I get this both mixture. All right. Then proton transfer. Remove that proton. Remove that proton. And the last step is the second step of Woodward dihydroxylation is hydrolysis with sodium hydroxide, something like that. All right. Again, these are my proposed mechanism. Never said it's correct, right? But at least you should be able to propose the intermediates that make it reasonable, that lead to the stereochemical outcome: syn-addition, anti-addition, and mixed addition. Okay. All right. One more thing. I'm sure before we go, right? You guys gonna look up things on the internet. Be careful. Be really, really careful. Name reaction, or like the reaction that you're not really familiar with. Those are it's a more like an advanced reaction. Okay, it's the mechanism probably known, probably not known. We never know. People say proposed mechanism. These are one of the proposed mechanism of a Woodward dihydroxylation. And I'm going to tell you, this one is, oh my God, do not use this source. Okay, give you some example. Take a look at that arrow. I see that arrow. I don't trust this guy. The double bond attack iodine. This iodine about to leave. These two electrons have to go to on iodine. It's gonna go away somehow. Well, we kind of like let it slide, kind of get an idea of what you're doing. But take a look at the next arrow. What are the? Where does that acetate attack? Attack the bond right there? No, this guy attack an atom, attack one of this carbon. Why this guy go to direct to the bond? Okay, that's another one I don't like. Try another one. What's going on in here? I don't even know. Somehow this oxygen is attacked, that carbon and iodine leaves, and I don't see any. I don't know what's going on. Okay, one more right there. This carbon is totally non-nucleophilic. There's no lone pair on that carbon. This carbon somehow attacked that bond. I don't know. I think they probably used a double bond attack. Anyway, I mean, just a bunch of arrows it doesn't make any sense. Okay, my point is, if you look up online, be really, really careful, especially the name reaction. There's no correct answer yet. And if you see the arrows like this, do not use this at all. Your TA will spot that and they know that. Well, it means that you don't understand how reaction works. Okay. All right. Be really careful on that. The rest, well, go to the lab and have fun. When you propose this mechanism, please feel free to contact the TAs. All right, they will help you out with the mechanism because I know it could be complicated, but they're there to help you. All right, good luck and have fun.